Hey everyone, good afternoon. Who all is here? Do we have anyone in the chat yet? Who all is in the chat? Anybody yet? Start talking about some partition models, Hey Zoe, what's up? What do you want to work on, Zoe? You name it. You name it, we work on it. I'm gonna reset Mubot here. Mubot, you gotta wake up. We can do some work. What are people wondering about? I sent out messages to 320. Today's a good day to do some work. We got someone over here in the chat. 475 chat, someone's in. Nice. Oh, got a lot of messages on Discord. Check out later. Which ones are you wondering about? Let me know which questions you're wondering about. We can take a look at those. Be like, how about this? Can you talk over how to do this? Oh no, sorry to hear that. Hope you're doing all right. Feel better. It's a cold and flu season. It is a busy time. It is a sad, busy time. So let me get the assignment up and going here. Which one are you wondering about? Got assignment number 8, multiple regression part 1. Download it right here. Our data file. Here we are. Oops, wrong one. Oh, that'll work. Ear infection, but I have meds now? Nice. Well, I'm glad you got some meds for it. Which parts are you wondering about? Let's go to the main screen. Let's check it out. So here we are with the file. Make sure you have both your data file and your RMD file in the same directory, and then everything should load in nice and neat right there. So what do we have? What questions are there? What are people wondering about? What question? 474 lab question: why we choose the and not the 0.5? Oh, so for question 2. Because question 2 says, let's go look at question 2. 2 seconds. Thank you, Sherry, for asking. I'll need to go find that. 474 question 2 says, question 2, tree-based models, says, the accuracy of the naive on the holdout. So the accuracy on the naive on the holdout. So that is the accuracy of the naive on the train. So it should be, well, the accuracy of the naive on the holdout. And so it wants the accuracy of the naive on the holdout. And if you hear that right there, Zoe, the naive model is a model we talk about in 320, which is the no knowledge model, the model that does not have. And so the accuracy of the naive on the holdout. Heyo, Robert, good to see you here. For some reason, I can't get my data loaded for the assignment 8. It says assignment 7 on my file. Yeah, it says assignment 7. I moved around assignments. Summary holdout churn gives that right there. So that's the accuracy on the holdout. That is correct, Shreya. You got it. Yeah. Yeah. That is the accuracy on the holdout. That is correct. That is the accuracy on the holdout. Does that... That is... Yeah, I think it has 2 answers. So, I mean, I can basically show it. I don't know why it has that second one. It might be because a different way. It might be because of... I'll show it right here. Like, it has 2 answers. And so sorry for confusion. Just I want to alleviate some of your confusion. I think it's maybe because of the way things can be rounded, or like not rounding. There's rounding and rejection. It's those will be loaded in. That's correct. If you see those in your global environment, you're good. So it's rounding. Like if you use rounding versus rejection, let me see if that's the issue. So and then let me know which things you're wondering about, Zoe, on this assignment. So here's where we're doing the naive. And we want the accuracy on the naive. So let's change this to RNG kind and go sample kind equals rejection. And let's put all this in one chunk so we can then run it, and let's only look at the holdout. So the holdout accuracy with rejection, oh, we don't have the churn anymore. Here, let's load in that. Oh, we got to load data churn. Data churn, there's that. And it's 85.4, and then the rounding, so we'll copy this just so we remember it, and then the rounding is that. So I think that's what it is right there, Shreya. So if you look at these two answers we have on the screen right here, it's because of those, and it's just happenstance that the train is also one of the others. So just because of the way rejection versus rounding goes, so that's why there's two answers, and that just happens that it overlaps with the train just because the numbers are very, very similar. So yeah, you could get it right by accidentally choosing the train. Yeah. And so how are you doing right there, Zoe? How are we doing with loading the files? And good question, Shreya, right there. Excellent work, Shreya. Does it get easier to code and know what the code is doing as we go through the classes? Set up a scatterplot matrix? Yeah. So to set up a scatterplot matrix, let's go check that out. So let's put a note right here, making a scatterplot matrix. Heck yeah, it does. That's awesome right there. Let's do making a scatterplot matrix. So here we go. Making a scatterplot matrix, BAS 320, and making a scatterplot matrix. Making a scatterplot matrix. Gets more routine, right? So when you make a scatterplot matrix, we need to have X and Y variables. So I'm assuming one of the first things is to make a scatterplot matrix with the following variables in there. So when you make a scatterplot matrix, let's remove out all this stuff from our global environment. We're going to reload the global environment, make sure everything loads in. Now, I'm more of a fan of, as everyone knows, library ggally. I think it has in it. Let's see, gg scatterplot. Scat matrix, look at that right there, scatterplot matrix. And we want to predict demand from average temperature and all the other ones from the data bike. Is that going to do it? It's mad about this. Let me look at the syntax of this really quickly. The syntax of this is as follows. It wants syntax of the data frame and then the columns we're using, and we don't need to use a color. So it really just wants the data set we're using. So it wants bike right there, and then we should be good, and it's going to make the scatterplot matrix for us. And it does put demand over there. So I preferably like to do this. I think the other one is pairs. So the pairs is the other function which had a syntax similar to what I was writing. Demand tilde dot. Data equals bike, and the pairs gives you this. So here's the differences. This one's a little bit nicer in my opinion, also gives the correlation values. How is this looking right here, Zoe? To set up the scatterplot matrix, you have to have library ggally to do the following function, but also this then turns into an interactive graphic if you want. But the pairs matrix is letting us see right here the pairwise combination of all the x's and the y's. Most importantly, you want to look at the relationship of your what variable with your what's is. Most important. That's why this one actually has a advantage right here. You want to look at does the dot donate all the x's? 1,000 points right there, Zoe. That is correct. Y tilde twiddle dot stands for y by all the x's. Correct. Good answers right there in the chat. The dot donates the y's with all the x's. And there's your y variable of interest, demand. And here's a plot of demand average temperature. Here's a plot of demand effective temperature. What does this plot right here represent? What does this plot represent right here? Because demand is our y. So this is a relationship right here. This plot specifically is a what relationship. This plot right here is a what relationship. So this is a YX relationship, this plot right here. This is a YX relationship, this plot right here. This is a YX relationship, this plot right here. This plot right here is a Y variable of interest with another X. This plot right here is a what relationship. So this plot is a Y with an X. This plot is a Y with an X. This plot right here is a y with an x. Well, it's two quantitative variables. It is, so it's a scatter plot. But here, listen to the phrasing. And good work right there, Zoe. This plot right here is the y variable of interest with an x. This one right here is the y variable of interest. Like on this axis right here, this is the demand axis. That's what this stands for right here. This is the demand. And then this is the effective temperature. It's got the axis way down here just because it doesn't have numbers crowding it up. But the axis right here on the bottom is the effective temp. So this is a what variable combination, this plot right here. Like this is a y with an x. This one right here is a y with an x. So this one would be a what with a what relationship. What variable combination? Like what like y's or x's? What is that? And this is a good review of last class. Like this is a big concept from last class. That plot right there are two x variables. So that indicates right there multicollinearity, or at least collinearity because it's two x's. So it's an x and an x. Great job, Meath, right there. Yep, that right there is an x and an x combination. So that's not actually a good thing. Think about this. Average temp and effective average temperature sound a lot what? So think about that. Like now we see that they're very similar, and just the wording, average temp, effective temp, temp, they sound a lot what? Like just thinking about it, be like, oh, average temp, effective temp. It's via the class link, so you can go to any of the announcements or any of the watch class live. So it'll just be under watch class live or the announcements, and they're all recorded. So they're not like straight on YouTube because I have them unlisted. So just if you can't find them, let me know. But they're unlisted. That way, it's just like if you're in the class, you have the links, and that way it's like kind of like little hidden away. So that way we don't just have random people. You notice we do get bots every once in a while on these streams. We don't get them in class. And I used to do just the streams as public streams, but then we got like, it's just, we got one or too many trolls and bots in class streams. If we get a troll or bot during a Kahoot contest or during office hours, it's whatever. We just throw them away. But during class, I'd prefer not to deal with trolls and bots. So I stopped doing the public streams. Now we do these as public streams. So we get every once in a while someone to be like, whoa, is this a stats class? What are you doing, nerd? I mean, one person was calling me a nerd. You're like, this man is nerdy. I was like, that's cool opinion. I am nerdy. That's true. Got my Mega Man right here. That's proof I'm a nerd. What else are you wondering? Meath, what are you wondering about this class? Or what are you wondering about this assignment? Let me know. What are you wondering? That's one part down. YouTube. Oh, thank you so much. Yeah, I like it way better because you can actually like pause this. You can rewind this. There's so much. We're broadcasting in 1080, so everything here should be high quality viewing on the screen. So like it's live 1080. So that's what I love about it. Like, so where is it? Office hours right here. Let me go live. I'm gonna hear myself talking. It's not gonna load. I'm grabbing too much internet. There we go. Yeah. Yep. That's awesome. Yeah, it's really clear. Seeing how it looks. I was wondering about the interpretation of not the adjacent, the adjusted. Good question right there. And that's one of the last things I didn't want to speed through. So let's talk about what adjusted R squared is. So think about this. If we were to talk about what happens to R squared. Yep, adjusted. Yep. What happens to R squared as you add more x's? So if we had an R squared over here, and if you go from 0 x's to 1 to 2 to 3 to 4 to 5 to 6 to 7, if you add more x's in your model, R squared will do with this. This is like from Stat 201. If you add more x's, R squared will start to do what? You can think of R squared from 0 to 1 or 0 to 100%. So R squared will do what if you add more x's? Hey, Evan, good to see you here. R squared will do what? What will R squared do? This is just like decision trees with more splits. R squared increases when you split the tree more or you do more, you put more x's in. So R squared with no x's would start at 0 because you're at the naive model, and then it goes up, and then it goes up. And this kind of looks like the split history, right? So if you've just done decision trees in 201, it looks like the split history. Now, there might be increases right here, but each x would add in new variation. So think about this. There's probably got to be a way to say maybe we should stop adding in x's. So what we have is a value called R squared adjusted. R squared adjusted is simply this. R squared adjusted is R squared with a penalty. The penalty is based on how many x's. Does that make sense? And great job, Evan, right there. We got 30,000 points for all this practice. The r squared is based on how many x's you add to the tree. Who follows that? So where would we have a greater penalty? Where would the highest penalties be with r squared adjusted? R squared adjusted is an r squared penalized for how many x's you add. We could look at the mathematical formulas, but that's the conceptual nature of it, is that you're now going to penalize yourself when you add in x's. So where would the penalties be the highest? It's for how many x's you add. So where are the penalties higher? The more x's, more penalties. So there's a high penalty over here, and then there'd be a low penalty over here. And actually, I think none, because the k equals to 0 there in the equation. So this would still just be an r squared of 0, no variation explained. And then we would see maybe here, I kind of did this, and then this, dash. What do you notice about r squared adjusted? What do you notice about r squared adjusted? R squared adjusted can go what? R squared adjusted is an r squared that doesn't always have to go up. In the output, do we use the multiple r squared or the r squared adjusted? So good question, Abby, right there. So the r squared adjusted is used to tell us, we don't interpret it. We don't interpret r squared adjusted, but r squared adjusted is a way to tell if your model is doing better by adding new x's. So what we oftentimes do is we compare our r squared adjusted to our r squared. So what would you want this value to be very close to? If you compare your r squared adjusted to r squared, you'd want that to be very close to what? So think about like right here, this might be an r squared adjusted of like 0.38 and an r squared of 0.40. You'd want it to be close to 1 because that says like you're not really getting penalized that much. So you want that to be as close to 1 as possible so that way you're basically having the same. What do you notice over here towards the end of this where maybe this is again around 0.38 and over here you now have an r squared of 0.58 or something, or 68 we say. So now, what do you notice about that? You might look at your r squared adjusted dropping because then you're just getting penalized for adding x's after you account for like, because x's will always explain. So your r squared adjusted is like, well, we're going to make it harder for you to win. So it's if you're getting real variation, this is for 320, which you notice it builds off 201 concepts. That's why I'm always like 201 is so important because this is just r squared adjusted. So r squared adjusted is just r squared adjusted for how many x's. So if you want to pick how many x's to put in your model, you should probably look at the what. If you want to pick how many x's to put in your model, you could probably look at the what. One way of doing it would be to look at the what. If you want to pick how many x's to put in your model, should you look at r squared or r squared adjusted and try to find where that's optimized? Would you look at r squared or r squared adjusted? Which of those would you look at? Oh, we should have marked this r squared adjusted. I think it's about here. R squared adjusted, exactly. Because it's going to be a penalized version of your r squared that fairly assesses if you're adding new variation being explained. It's that is the penalty. Great job, Meath, right there. That is the penalty. That is how much you've been penalized. Nice job, Meath. We got 3 points for that. That is the penalty. That gap right there is how much, because r squared adjusted is just your original r squared minus the penalty. So that is the penalty. Great job on the conceptual nature of that. So that is the penalty. And a lot of times with lower x's, there's a small penalty. There's some other things that come into play, like sample size and how close you are to the top r squared. But the more x's you add, the more penalty there is. But if you're adding good x's, the penalty will be small. If you're adding bad x's, the penalty will be large. So it'll stop you from adding variables that you shouldn't add. Does that make sense? Like if you add bad x's to your model that just don't help, you know what can actually happen? What's the lowest r squared to see? What is the lowest r squared possible? What is the lowest r squared possible? The lowest r squared possible is what? Is 0. So let's say you have a model that is really, really bad, and your model is doing like this right here. R squared's lowest value is 0. So R squared adjusted is R squared with a penalty. Guess what R squared adjusted can do? R squared adjusted can do what? R squared adjusted, because it's R squared with a penalty, R squared adjusted can be negative. So it doesn't have an interpretation. It's not percent of variation. It's a fairer, like that's the interpretation if there is one. It's a fairer way to assess how we are doing. And what would you suggest to someone about their X variables here? If you saw this right here and you're like, ooh, what would you say if you saw this? So if you saw this R squared adjusted where the values of R squared are just going negative, I know, right? Like,
Wow.
what would you say? You'd be like, yeah, it looks to me like maybe your X is what? Yeah, your X's are really bad. Like these X's really don't help explain why. Also, the p-values for the X's are probably super high. Like the X's are probably not statistically significant. The R squared adjusted shows that we really shouldn't be adding the X's because after we adjust a penalty onto the X's, this is just a bad idea to add them. What other questions are there? So R squared adjusted is a fairer way to look at the R squared after we penalize ourselves because R squared will always go up, but R squared adjusted will be penalized. So R squared adjusted can be used to examine where should we stop adding X's. Does that make sense why we have it? This wouldn't be well, we'll start to get more multicollinearity as we have more X's because the X's might step on each other's toes. We could talk about multicollinearity if you want, and I could do it towards the assignment questions, which we did see some multicollinearity. Can we do Q1D? Yeah, let's look at some Q1D. The multicollinearity is going to be coming a lot from here because this is average temp with effective average temperature, which is a collinear relationship, co meaning 2, multi meaning all the X relationships. But this has a high amount of collinearity, 2X relationship, and there might be other X's that have relationships with it too that are explaining it. So 1D, let's look at 1D. 1D says fit a regression model using these 4 predictors, examine the results. How do we fit the 4 predictors? How do we fit the 4 predictors right here? We've already got a code that kind of works for it. How do we fit a model with the 4 predictors? And we're pretty much good to go. How do we fit a model with the 4 predictors? So let me take a note. LM, use that's all I got to change, right? LM, Y tilde dot. Now the reason we are using twiddle dot when it says the 4 predictors is the Y variable's been defined as demand right here, and then the twiddle dot is saying all the other X's. This stands for Y by X. It is one argument right here, which just says write the formula, and the formula we are writing is going to be the Y variable by all the X's, Y twiddle dot, and then the data equals the bike data frame right here that says where do these X variables live, and the Y also, and we create the model. Now we just run summary on the model to create it, and then we've got questions. Questions. 1, 2, 3, 4, 5, 6, or just 5. There we go. So which of these should we talk about? I'm gonna try not to give the full answer. Yeah, Charlie. I think this is, and Meath and Zoe, is it starting to come together? Do you see, and Abby too, are you starting to see a lot of the same things? Like, this is where I hope it starts to feel like we're doing the same thing a lot. Like, wait, we're going to summarize it. Wait, we're going to check regression it. Wait, we're going to visualize it. Yeah, it starts to, like, the end of the class is where it's like very repetitive. And so when you understand how to interpret R squared, we'll do it 1,000 times. So that's what I really like right there. It really just starts to make sense. And Zoe, you know I like hearing that. You know what we did? I'll show you this really, really quickly. At the very start of class this morning, someone said we should look at a stock. And where did we do that today? Did we do it over here? Wait, that's the Eat Jelly Beans one. Don't tell me I closed it out. No. We were looking at a stock. What stock was it? No. Oh, it was right here. Here we go. So check this out. We've got tidyquant, and someone said, anyone name any stock you want. Does anyone know a stock ticker you want? Can we do chapter 13? Yeah, we do some of that. Name a stock you're interested in. I'm going to call it my stock. Tesla. Watch this. You ready? What's even better is if I go right here and we call this stock name, and I grab all of this, and we go function, and we say plot stock, and we go into here and say stock name equals TSLA. Drop this in right here. And plot stock. Stock name not found. Oh my gosh. Look at that. And there you go. Ooh, what's happening with Tesla? That's Tesla this year. And I've just created a function right here for plot stock where I can put in any stock and I can see what's happening with that stock this year. So you name a stock right now and I can plot it inside of R just like that. Just like that. For your stock. Say what's going on with such and such. Stop. There you go. Oh wait, wasn't just changing my thing? Oh, I got to rerun the function. There we go. Where did you pull that data from? Oh, it's is it interactive? I think we can't make it. We're trying to make it interactive. Let me try to make it interactive real quick. 2 seconds. Library. I don't want to take too long on this. We could almost make it interactive. The answer is, come on, work. Yeah, it's doing this. I'm moments away, Meath, from making it interactive. But if you give me a little longer, I bet I could make it interactive and make it as easy to grab a stock just like this. And we could change the dates on it. California Exodus. Oh, the one coming up here. But this is the kind of stuff that we want to be able to do. And think about, all I did was take all my code right here and turn it into a function to grab your stock. Yeah, good one. Oh, we'll do it here, Evan, soon. Yeah, so this is what we do in 475. I like to do stock projects and stuff like that, and you get to plot stocks and, talk about them and do these Bullabong bands, whatever they're called. But just think about this, like, you can just check your stock. You could have this email you once a week. Like, you can get R to email you. I don't have that set up, but you could have R run a report once a week for you and email you that report and tell you how your stocks are doing. Like, you could wake up Monday morning to weekly stock reports from R. So like that, I don't know. I think that'd be pretty cool. So like, I guess you would need to, but probably have to run on a virtual machine. That might be how to do it. You might be needing to run a virtual machine with R running in the background, running a code that checks the time. And then when the time hits, like so much time has passed, it sends you the report. And maybe you could have multiple reports running. Yeah, like you would just have a virtual machine running a check on the time, and then when the time amount has passed, it will then create and email you out a report and say like, here's your stock report for the week. It will just like create file, send file. It's crazy. And then you've just created your own email chain server of getting reports for yourself to wake up Monday morning and just be like, let me go look at my reports. And so you can just have an analyst working for you that you created. That's where the real power is. And maybe, I don't know, maybe we should just like show people how to do that and create that in a class. That'd be pretty cool. Because I know all the components of how to do it. I don't know. I don't watch my daily stocks. My dad's got stocks. So which parts are we wondering about with this one right here? Freshman Zoe would be shocked. Which questions are you wondering about for the bike data right here? Is the model itself statistically significant? Quote the relevant p-value. Report the value of R squared and interpret this number. Some 201, right, Evan? R squared, interpret the number. Also, the significance of a model, it's not slope this time. Not slope this time, because slope is in the simple world. Report the R squared and discuss why we use it rather than R squared, the R squared adjusted report. So we know where that's at. Report the typical error made. What is the typical error made of the regression model? Where do we see typical error? I'm not quite showing the answers because I want you to find them. But where is the typical error of the model found? You can put it in the chat if you want, then people can find it in the output. RMSE, the root mean squared error. So when you think about this, this is a really cool thing to know right here about root mean squared error. So that is root mean squared error. Now, another preference people have is MAE. What do you think the last letter of MAE is? Like if I tell you it's mean absolute, what do you think the last letter of MAE is? It's all error. So all these things right here, which are other metrics people use, the whole point of all of these is to what? The whole point of every one of these metrics, we don't use all of them. We just use RMSE, is to understand what? The whole point of all of those is to understand what? The whole point of every one of those is to understand the what. Just repeating the same word now. Like every one of those metrics is just a way to understand error. Some of them are absolute error. And you think, why do we do absolute error and why do we do like means of it? Like they also all have means in it. They all have means and they all have error. So these are the common themes, is to understand the typical miss the model makes. That's the goal. Now we are going to use RMSE. Now, why don't we use SSE, which is sum of squared error? So when you look at this, this is also an error calculation. So why don't we use standard error of the regression? Oh, yeah, Evan, in 201, if you look at the jump output, that's the standard error, I believe, right? Great job, Evan. If you notice that in the output, jump also reports that. I think it does. And, well, the sums of the squared error will be in squared units, and it'll be a mass quantity of sum. Mean error can't be used, and that's what Meet's talking about right there. We can't use mean error because mean error cancels out because some residuals are positive and some residuals are negative. So mean error would always be 0. So we can't use mean error. So mean error is like can't use because the mean error of a model is 0 because points are above and points are below. To Evan's point right there, if you look at a regression model in Jump and you make a simple regression where we just predict something like this with something like this and throw it in, we make our regression model fit the line. And right there, well, no, there's the RMSE right there. There's the root mean squared error. That means when we predict somebody's age, we typically miss by about 1.4. When we predict somebody's age, we typically miss by about 1.4. If you had to guess the age of a college student, what would you guess? If you had to guess the age of a college student, what would you guess? If you had to guess the age of a college student, what would you guess? That's what I would guess right there. If you had to guess the age of a college student, what would you guess? 20. And what am I showing in green right there? Green, I'm showing what visually? I'd probably guess 20. Because think like you go to college 18, 19, 20, 21, 22. God, it's weird to think that a lot of seniors are like 21, 22. That's the naive model, the naive. So the naive model right there is the mean, and it's very close to 20. Wish we could see it. We could mathematically find it. Yeah, it's like 19.8 or something like that. That's the naive model. Some of them I might say 16. There are people in college who are like 16. It's there. There are people. Yep. And the naive model would predict 19.7. So think you're typically off by about 1.4. So I mean that kind of has the bounds of almost 18 to 21, right? Especially when I'm 21, so it's funny. I ask people to guess my age sometimes, and I get age guesses all the way from like a guy looked at me and he goes, I'd guess a little bit older. He goes, about 27. And I was like, thank you. That was like, when he said I guess a little bit older, I was like, oh no. It's like, I'd guess a little bit older. 27. Yeah, I'm 27. That's all good right there. Need to put filters on to get away all the crow's feet on around my eyes. He said I was 80. Love it. Okay, so those are the errors. Is this, in your opinion, is this model used to your own data or 22 and a half? How dare you? I should have told him, I was like, I'm 24. You're like, oh, wow, it's close, right? I was like, no, I'm 40. Oh, man. I think, Zoe, what else are you wondering on this? I don't want to do everything, but I think we know, like, tell me which ones you're wondering about. Write out the fitted regression equation. We did this. Check out last class, especially. We write out the fitted regression equation where we do this plus this plus this times this plus this times this. Extremely important. Interpret the coefficients of average temperature. I'm actually going to do one of these right here because this is huge for the test. In tool 1, we do interpretations. So let's put here interpreting coefficients part I. Which one's part I? We'll let me put that here, part I, and then Evan, remind me we are going to do yours coming up here next. Part I. So let me go right here and mark this. This is part E. So 3813 BAS 320. Question 1D part E. And then question 1D part I. Okay. So when we interpret coefficients, let's look at one of my favorite data sets to work with right here, which is the, if you've come to class, you've probably heard this one, but we are going to look at the body fat data set. And in the body fat data set, we are predicting somebody's body fat. So I'm going to use body fat data set 1, and it has the more variables, I believe it does, and we see them right there. So let's predict somebody's body fat. If you gain weight, your body fat generally does what? Just think in the univariate world. In the univariate world, if you gain weight, your body fat generally does what? You gain weight, your body fat generally goes up. Great job right there, Evan. So this is how we make the model right here. And then we summarize the model and we take a look. The model is statistically significant. And here's how we have to interpret it. Get ready. 2 individuals who differ in their weight by 1 pound are expected to differ in their body fat by 0.16, where the individual with more weight is expected to have a higher body fat. I'll repeat that again. 2 individuals who differ in their weight by 1 pound are expected to differ in their body fat by 0.16, where the individual who weighs more is expected to have a higher body fat percentage. Does that make sense? So Meet and Zoe and Abby right there, make sure you know that. That's the univariate. There's a small change in the multivariate world coming up. And this is the advanced interpretation, Evan, that is very, very specific, where we say, you know, if we have 2 people and they differ by 1 pound, well, then I'd expect them to differ in their body fat by 0.16. With a person who weighs more, I'd expect them to have the higher body fat percentage. But let's go over to the multivariate world right here. So all we're doing is copying our code. And then all we do is change that to a dot to mean all the x's. And we call this model 2 to save into. And we run the code. And now the coefficient of weight is what? Now the coefficient of weight is what? All of a sudden now the coefficient, which is the estimate, is what? The coefficient of weight is now negative and also not statistically significant. So the differences might actually be, we're throwing Evan 10,000 points right there, learning the, and if you do, well, I guess we should have learned that yesterday, right, Evan? But that is the advanced interpretation for 320. If you do take 320, you're ahead of the game right here. And all you have to do, Abby and Meet and Zoe, do you want to tell Evan the only thing that you have to do? And Abby has it right there. In the multivariate world, you just have to acknowledge that 2 people who are otherwise identical but differ in their weight by 1 pound. So think about this. Thank you so much, Meet, right there, helping out with slope interpretation. So think about this. So Evan, if Brian gains 100 pounds, you'd expect Brian to do what? Just over here in the univariate world. If Brian gains 100 pounds, you would expect Brian's what to do what? If Brian gains 100 pounds, you'd expect Brian's what to do what? And you'd probably expect about 16%. Like, now this isn't talking about change, but if there is a person who weighs 100 pounds more than Brian, you'd expect that person to have what? To be in technical, like 2 people who differ by their body fat, 2 people who differ in their weight by 100 pounds, we'd expect them to differ in their body fat by this. It's not meant to be change of an individual. Dr. Peachy would be screaming at me right now. Hopefully he doesn't see that part of the video. He probably sees it now. So he'll be like, Dr. Peachy says out, Brian got it wrong. It's not about change of an individual. It's about 2 people. We have a person here, person A and person B, who differ by 100 pounds. The expected difference between those individuals is a difference of, if they differ by 100, we would times this by 100, and it'd be 16% body fat. 5i, we can talk about that. Yeah. We can take, I think it's a partial F right there. Good job, Robert, going over that. And so now when you go down here, here's what this means, Evan, in the multivariate world, and to Abby and Robert and Evan right there, everyone, Meet too. Now it's 2 people who are otherwise identical. And I think, Evan, you are just seeing this right here totally, because if they're otherwise identical, they have the same neck measurement, the same wrist measurements, the same abdomen measurements, they have the same bicep measurements, but they are otherwise identical. So if you have two people who are identical, but one person weighs 100 pounds more, you probably actually would expect them to what? If you have two people who are identical, like same measurements, they're the same age, the same height, the same neck, but one person weighs 100 pounds more. So literally same measurements, but then I weigh 100 pounds more than the other person. You probably would expect me what? To be stronger, right? You have to be more compact. So if you were to weigh 100 pounds more than someone and be otherwise identical, and that's what we acknowledge here, we say two people who are otherwise identical but differ, and we could say by 100 units of weight, because then we would just times it by 100, would be expected to differ by body fat by 8%, where the person who weighs more is expected to have about 8% lower body fat. Does that make sense? I'm timesing it by 100 to interpret it in 100 units. Two people who differ in their weight by 100 pounds but are otherwise identical, just times this by 100, move decimals over. The person who weighs 100 pounds more is expected to have lower body fat by about 8%. And this is where we get into the statisticians just give their own interpretations. It might be due to them being more compact. They have the same measurements. They're otherwise identical. So that's the most important thing in the multiple world, is to acknowledge otherwise identical. Like you have literal person A, person B, they share every characteristic the same, but they differ in this X by, usually we just do a 1 unit difference. But 1 unit difference is so tiny. Say two individuals who are otherwise identical but differ in their weight by 1 pound are expected to differ in their body fat by 0.08, where the person who weighs more is expected to have lower body fat. And if you get it down where you can say it like that, you know the tests. You're good to go. How does Meath, Abby, Zoe, Robert, how's that look? And Evan, good job practicing this right here. How does that look? Evan earning everyone some big points. If you take 320, Evan, you'll know how to do these interpretations. Sounds good? Yep. And so that's why the multivariate world is interesting. And what might you think is the problem with some of these measurements? Really quickly on this, and then we'll look at I. A lot of these measurements are very similar. Like if I measure somebody's bicep or their wrist and their forearm, what do you think is going to go on with wrist and forearm measurements? Like somebody's wrist and forearm, which are X variables. You ready to take this? Somebody's wrist and their forearms are probably which are X's. What am I alluding to by talking about this concept right here? Like your wrist and your forearm measurements are probably very whatly, along with maybe even bicep too. Like all these measurements they're probably all sort of what to each other, which we'll see. I'll run the analytics on that. They might be redundant, right? They might bring the same sources of information. So abdomen's a pretty unique one maybe, but they don't bring new information, right? So this is variance inflation. And it's M2. Okay, there we go. Variance inflation, and actually the most redundant is weight, I think, right? And we could sort this rather. So you can sort your variance inflation to figure out which one's bringing the most redundancy. It is weight. Hips and abdomen, I mean, just think those right there are kind of similar. Like your hips and your abdomen are like literally next to each other in your chest. So we see a lot of stuff. Interestingly enough, forearm is not as redundant. Height has very little redundant information, so does ankle. But ankle might just not be good by itself. Like the ankle measurement is not statistically significant. It also isn't really redundant with the other X's. And the high cutoff for variance inflation is going to be about 3 point something. No, 2.6. Yeah, let's find out. 1 over 1 minus r squared of the model. 3.77. So we have these many variables right here with too high variance inflation. So everything from neck and on. And does this invalidate the model, Meath? Is the model done? Are we saying, nope, can't use this model? Should we? This is the last thing I'll say on this, and we'll do I. No, it doesn't invalidate the model. Multiclinarity does not invalidate. What is your skincare routine? No, my skin is, I do not have good skincare routine. I got dry skin. I don't got good skincare routine. Oh, you're talking about like because I'm old, maybe? My skincare routine is carry an umbrella when I go outside to play Pokemon Go. I'm not even kidding. People might think you're crazy that you carry an umbrella, but let me just tell you this: you only get one set of skin, so carry an umbrella. That's what I say, because the sun. I don't know if I'm lucky that I'm so pale, but I don't like the sun. Meath, do you think we should remove abdomen? The reason I say I don't know if I'm lucky, I just avoid the sun. Like if I could tan, I might be like, oh, the sun is so great. I'm just gonna tan every summer. But now I'm just like, sun's out. Ah! Do you think we should remove abdomen, Meath? Do you think we should remove abdomen? Or Robert or Abby, do you think we should remove abdomen? I'm trying to trick you. Yes, Meath, perfect answer. Abdomen is super duper significant. It has a lot of overlap with the other X's, but it's actually our most significant variable in the model. It with all the other X's in the model, it's like bumping arms with them, and it's like, hey, look, I'm the best. It is the best, but it's overlapping a lot of the X's, which not good. But abdomen is super significant, even though it has a lot of shared variation. So you don't want to look at multicollinearity and be like, hey, we got abdomen is kind of walking on the toes of the other ones. Get rid of the abdomen. so you should take out if you were to consider, and I think this here we'll look at, if you were to consider taking stuff out, you'd probably want to do, first off, you'd want to go for your knee measurement. You can take out 1x, but if you take out 2, you must run a what? To take out 2 or more x's at a time, you have to run a what? 10,000 point question. To take out 2 or more, to compare a larger model against a smaller model, you can take out 1, but once you start taking out 2 or more, you have to run a what? To see if you can. And I'll do that right here. And if you can tell me the name of this, and I'll do it as we run it right here. So let me go and grab this. Let's take out 2 x's. We'll say remove knee. So you can actually just remove knee like that. Partial F. Meath has it right there. Partial F. So this is not the full F test to test the significance of the model. And it's a partial, or sometimes we say simple versus complex, which is a partial F, or a partial model is a good way of describing it there too, Abby. So the next least significant was it could be ankle. It's height. Okay, I think it's height. Okay, let's remove out the 2 least significant variables. And let me mark this here as partial F. We kind of did partial F. Oh, is it chest? Oh my gosh, Meath. You got it. I got 3 more points for that. Correcting Brian points. 3 another 10,000. Correcting Brian's worth a lot of points. Thank you so much, Meath. Right there. It is chest. Second highest p-value. We just overrode our model 2. Let's call this simple. And let's call this the complex model. You can call it anything you want. But conceptually speaking, a partial F compares a simple to a complex to see if we should go from the simple to the complex. And the answer is, wow. Should we remove both those x's? Should we remove both those x's? Should we remove both those x's? Yes or no? The answer is a resounding what? The answer is a resounding what? A resounding this. What does that p-value mean? So what the p-value means right here is when you do the partial F, you're asking, do I have a statistically significant difference? Okay, so be more, explain more detail, Abby, because you might be right, but I want to make sure. So the question is, here's the question this asks. Question of the code is, do the x's bring with them statistically significant information? So if you're answering that question, you've got it correct. So do the new x's in the complex model bring with them statistically significant information? No. Does that make sense? So what's the choice right here? The x's do. The x's do not provide, not so much, this won't look at unique, just looks at statistically significant. It might overlap with unique a little bit, and you are correct, keep with the simple. They do not provide new information not accounted for by the other models. It doesn't really look at the overlap, which would be variance inflation, which overlap would interfere with that, because it could be that height by itself is statistically significant, and height is not statistically significant by itself. It could be that chest is statistically significant by itself, so chest probably had the overlap problem. Does that make sense? So chest was significant by itself and height was not significant by itself. It is possible in the multiple world for something that wasn't significant to be significant. So chest could have been significant if it did something the other variables weren't explaining. Like when we throw a party, it's significant for people to bring napkins if there's already pizza, chips, and dip. But is it significant to bring just napkins to a party? So if you bring just napkins to a party and you're like, hey, here's napkins and plates, and they're like, did you bring anything else? And you're like, nope. And they're like, well, what are we going to use these with? They're not significant by themselves. So it is possible for something to be not significant by itself, and then in the multiple world be significant, like it does something the other variables are not, and it accounts for sources of variation that we need accounted for. Because height does account for little less than 1%, but maybe we're at 99% R squared, and this gets us to 100%. So it is possible that this could be super important if it brought in like the new information we really need to get to like 100%. Does that make sense, Abby? That's more in depth on it. So we can remove. So to the question right there, we can remove because the simple model, do the X's bring with them statistically significant information? No, they do not. So keep with the simple. They're very specific on this. Like, so do the X's bring with them statistically significant information? No, they do not. So I would not put the X's in the model. Does that make sense, Meath? So this tells us if going from the simple to the complex brings with it new information, and the answer is no, because it's saying, should we use the complex model? If it's statistically significant, we would say yes. If it's not statistically significant, we would say no, because it's the amount of variation explained by the new X's. Awesome. Let's look at that I right there. Thank you so much, everyone. And Robert will do yours, and then Evan will do the question. Thank you so much. I says, explain. Let me grab this right here. Oh, this is a partial F also. Justification of removing. So I think this kind of has it, right, Meath? So this is part I, which is also a partial F. So if you're wondering and watching this, please check out what we just talked about. Let's see if it covers it. Explain why we would be justified in dropping average temp from the model, but not both these right here. So can we just remove one thing in and out of the model? Can we remove one thing in and out of the model? Can you just take one thing and remove it in and out of the model? This is a great note to have. In regression, can you just take one thing out of the model? Can you? Can I just look at someone and be like, let's take that out of the model? Can you? Yes, you can. Watch this. I'm going to remove just height. Do you see height right here? Let's say I were to remove just height and run a partial F on just height being removed from the model. Now, I'm going to think really, really hard on this. Okay, so now I'm going to think about the p-value on this. You ready? Okay, here's the p-value. 0.46830. I think that's it. That's my guess. Oh, a 0 at the end. I'm seeing a 0 in my head. 0.46830. Let's see how close I was in my guess of it. Oh my gosh. Whoa. How did I guess that p-value? How in the world did Brian... before I even ran the partial F, I knew the p-value of it. How did I guess that p-value? How did I know what the p-value of the partial F was for removing one X? So this is just one X. How did I know that without... before I ran the partial F, I somehow knew that. Did anyone see what I looked at? If you were to run a partial F, the p-value is just the p-value of the model, the X in the model, because that's what that X does with the other X's in the model. So that is actually a partial F of 1. So you don't have to run the partial F if you just remove one thing in and out, because you already know the p-value of it if you were to do that. But if you remove two things, that's where we do not know the combined power of removing two things. Like if someone says, could we remove height and neck? Well, then we have to create a simple model where we remove both those. Now, neck is statistically significant, but this is asking, does a model with height and neck in it explain more variation? Great job, Abby, right there. And the answer is no. You would actually be justified for going to a simpler model without height and neck. You could actually remove both of those, and your model, you do not get statistically significant reduction in sums of squared error with a model with those. So do the X's bring with them statistically significant information? The two X's we remove do not, as a team, bring with them statistically significant information. Does that make sense right here, Meath? So if you want to look at comparing a model without two variables, you have to remove them together as a team and then do the partial F of the simple to the complex. So if you're looking for more examples of this, check out what we were doing prior and you'll see more examples. So that should help with that. And then Robert had one too, right? Robert, thank you so much, Robert. Which one was Robert worried about? Is there any chance you go over 5i? 5i is 5i right here? Oh, wait, 5i. Is it, which one is it, Robert? Which one? I don't see Robert's question on here. Wait, is it 5? Oh, 5i right here, 5i. Okay, did we just do that? Yeah, we just did that. Wait, we just did that. Good stuff, yeah. Where do you go? Question 1D. Is this 1D or 5i? 5D, 1i, 5ID? I think it's got it. Well, 5i. Did we get it, Robert? We'll do coffee cereals here. Oh my gosh. I gotta wake up. I gotta do some book work later. Okay, let's do a little 201 to end off. So Evan, thank you so much. I hope you take 320 because you've got a knack for it. You were doing some great stuff right there. Really big shout outs, great work. Understanding a little bit about multiple regression. If you look, it all just builds off what we do in 201. So that's why I'm like, if you understand 201, because Meath, if you want to, hey, Ethan and Evan, Meath, do you want to talk about like 201, 320, like the knowledge, how it, anything about that? The muscle thing was all me. Oh yeah, you got it. If Meath has any comments about that, let us know, because I know you might have some really great insight for anyone who's interested in the doing 320. So we want some confidence intervals here. It's gonna be some equations. You know what's really cool? Watch this. If you want to do confidence intervals in R, check this out. If you want to do a confidence interval in R, if I go out and talk to 100 UT students, and of the students, 40 of them say they eat at Taco Bell. So 40 students say they eat at Taco Bell out of 100. I'm 95% confident the true proportion of students who eat at Taco Bell is contained in the interval 30.47 to 50.29. Done. That's it. Are we still launching G Fuel MuleBot? That'd be cool right there, Ethan, right? So that's how to do it in R right there. Just like, know your notation. That's what every question is going to boil down to for the remainder of the semester, is knowing the notation. Know the notation. Know how to interpret it. Know what these things mean. Know why we're doing it. Know the notation. Which question is it that you're wondering about, Evan? Can you repeat it again real quick? Which question are you wondering about? Which one was it? Notation, brother.
Notation, brother.
All about that. Which one are you wondering about? Oh man. I am gonna sleep. A poll conducted. Oh, I literally am on it. Boom. Okay, a poll conducted. So we're gonna do this the easy way, and we're gonna do this the hard way. What's interesting, and this drives me a little bit crazy sometimes, so let's go here. 10103 stat 201. This is chapter 13 again. Chapter 13 quiz. A poll conducted. Time to learn right there. And then Evan wants the California Exodus. Ooh, and you got the thing up there. I like that. So what is the notation right here? Let's mark the notation. The notation for this is what? What is the notation? Help me out right here. It's all about knowing the notation. Yeah, maybe. Yeah, just relaxing right here. Some points. What is the notation? Can anyone tell me any of this notation? Read through the problem right now. See if you can. This is where you want to make sure, if you're working on this, that you mark your notation. It says 2019. That's just a year. We don't need to worry about that.
It doesn't matter.
I love that. 52%. So a study found out that 52% of people, of these respondents, that is N. So this is N. And 52% is not the R squared, not the correlation. 52% is the what? So they said they are considering moving out of state. That's the percent of people in a sample who said they're moving out of state. So what would that be in notation? That is the percent of people in a sample, who said they're moving out of states. That's the hint right there. That is the percent of people in a sample who said they're moving out of state. The percent of people in a sample who said they are moving out of state. The percent of people in a sample who said they are moving out of state. Close. But remember, percent of people in a sample. This isn't the truth, though. So, Evan, good work out there. Percent of people in a sample proportion. The percent of people in a sample. So 52% is what? Make flashcards with these if you want, where it says like sample proportion. So Y bar is sample mean. This is P hat. No, don't worry. Good questions right here. P hat is sample proportion. P is true proportion. We don't know what the true proportion is. Y bar is sample mean. Mu is true mean. No, good guesses. This is Evan. I can't tell you how much I appreciate you just trying. Like, you just got to practice. Like, don't worry. A lot of people, you're going to see people in class. Wait, what's Y bar? What's mu? What's P? What's P hat? And these are on the finals. So that's good news. Just practice. So the notation is going to be key because it says making 90% confidence interval. So we need to solve the formula P hat plus or minus Z star P hat Q hat over N. So what is one thing we're currently missing that we can find like that? Square root. Forgot my square root. What is one thing we are currently missing? I'll talk about that in a second. Good question. Z star is the confidence, the critical level for a 90% confidence roll. Tests will say use Z 1.645. I'll show you how to get that in a moment too. It is the Z score for a 90% confidence roll and the critical level at which we cover 90% of the curve. So what is something we have P hat? We have N. So, and I gave you Z. So what are we missing? And we should be able to find it. And how do we find Q hat? Once we find Q hat, we got this. We just plug in the numbers and we do it. Solve it. You're right. You got it. Yep. It's just going to be 1 minus P hat, which is 0.048. And there it is right there. And 0.52 times 0.48 over sample size of... It's like, where'd that go? And if you're wondering about the p-value, the z-score, where do you think we will go to get the z-score? Where do you think we will go to get the z-score? The 90% is relative to the z-score. So we need to go to the David M. Lane applet. You can also write these down, and we give them to you on a test. So we need to go to the David M. Lane applet and go to the second button and put in the middle 90%. So there it is right there. That is the middle 90%. And as we go up in z-score, or as we go up in percent, the z-score gets bigger. And these are some values we use right here. It just covers more of the curve. So you cover the middle 90, and that's the z-score. So the star means relative to a percent. Does that make sense there, Evan? So this is the z-score of 1.645. You weren't supposed to know it off the top of your head. Yeah, and it's 1.6449, I think, to be more exact. So, but it's 1.645. But that is the z-score right there in classic statistics, 1.96. Wow, 1.95996 with classical. Anyways, I gotta stop. Basically two. So here's the formula right here. We just go through and solve. This is the margin of error. This is the estimate. So it's an estimate plus or minus a margin of error. And those are important terms we'll be talking about a lot, the margin of error. So the margin of error right here is being calculated as we speak, just plugging in the numbers. Don't make errors. There is the standard error. And that's the critical value right there. So the margin of error is made up of the critical value times the standard error. And there's the margin of error. And the estimate is this. And so now we just go plus or minus. Does that make sense, Evan? How are we doing this right here once you solve it? Is the answer to the question. It does want it as a percent. So we need to times this by 100. And then we go 52 plus this. So what's it want to one decimal? 53.2. And then 52 minus this is 50.8. As long as we carry decimals, we should be good. There we go. Now, what's really great, and then we'll look at that question in a moment. What was the 4527? Is it level? Unused argument. What is... No, it's confidence showing. Prop. I forgot what the thing is called for this. Conf level. Did they change that? I thought it was level. There we go. It's bigger. Is it? No. No, that's it. 53.2 and 50.8. Yeah. We could probably get that out of it by going here and storing as X. Or let's say answer. And run answer, $, confident, and there's the interval. And pull from it list 1. No, that's the one first element. Oh, really? Oh, sure. And then we'll put it in a vector. And we'll go here. We'll vectorize it. And times by 100. And there you go right there. And then we'll take the answer, last but not least, and round to 2 decimals. So this right here is the answer. What does yours say, 90% or 95, or what does yours say, Evan? I see you said, oops, you got yours wrong. But this is how I would do it inside of, or did it say 1 decimal? Is it 1 decimal? 95%, 1.96. So the z-score for, so you'll use z-score 1.96 for 95%. So 1.96, make sure your mathematics has the values in here as seen. And then the z-score for yours will be 1.96, not 1.645. My z-score is smaller because I'm 90% confident. So I have a smaller z-score. How's that doing, Evan, right there? 1.96 for your z-score. And the last part of this question says, interpret the interval in context. I am 95% confident, or 90% confident that the true proportion of people who will move out of state is contained in the interval blank to blank. One is blank percent confident. Nope. One is 90% confident that the true proportion who consider moving out of states is contained in the interval. There it is. 50.8 to 53.2. I did that and I calculated again. I still got it wrong. Kind of. Tell me your numbers, Evan. Tell me your numbers. What is? So we got another part to it. What are your numbers? What are your numbers for the proportion, and what are your numbers for this? Since the cost of living can it be reasonable to show that more than yes, because it's not in the interval. Since the interval is greater than 50%, the state's government should do this, right? Because they're considering doing it if it's more than, if it can be, yes. So they're going to do that if it's reason. Okay, let's check out. That's a good question. Okay, so yours is 50. It says that the proportion is 52.1. Here, we'll just run it with the analytics. Your numbers should be 95% confident. So I'm going to run it here in R. If you have 52.1, 4527, same number there, and 95% confidence, are your answers very close to those right there? That should be close to it. And then I could check the work right here. I'm going to check it right here. So here's me checking it with 52.1. Q is going to be that. P times Q over N square root. P times Q over N square root. It should be. It's all the numbers are the same. Like this is the same sample size times 1.96. There's the margin of error. And then we go here and do times 100. There it is right there. And 52.1 plus this. So there's the top number. 52.1 minus this. There's the lower number. Why is the 50.6 not negative? Because it's 52.1 minus, if you can see it right there on my calculator, 52.1 minus this, so it won't be negative. Because you're doing 52.1 plus or minus the margin of error. Yeah. So it's not negative. You're just saying plus or minus this amount. So you're just going your estimate plus or minus that right there. Oh, you can't see because I'm too zoomed in. Does that make sense? And then you have to times it by 100 because it wants it as a percentage. So when you get your final answers. Oh, no worries. No worries. That's once you get practice, it really boils down to notation for these questions. Like the constant thing I'm saying is we have to practice the notation. We have to know how to read the problem, how to know the notation, and then plug it into the formula. And then if you understand the problem, it's like we went out and polled people and asked them the proportion of people who do this. Then we can get the question right and be like, oh, they want a confidence interval for the proportion. So we go and look at the formula sheet, grab the confidence interval for proportion formula sheet, know the notation. P hat is sample proportion. Z is the critical value we use to calculate the interval for the percent confidence. So for this next one, how do you interpret an interval for this? One can be blank percent confident that the true proportion of people who will move out of state is contained in the interval blank to blank. I like to say I am blank percent confident that the true proportion, and it'll be true mean, true proportion, true difference, but that's what we're trying to estimate here. And then we can look to see if a value is in the interval. It makes everything easier later. Yeah, exactly, Amanda. Yeah, that's why I try to be like, know the notation, know why we're doing this. And great job, Amanda, right there. We're going to start class in 9 minutes. So until then, it's good to see you here, Amanda. Good to see you here, Evan. Everyone, 8 minutes till class. Bye for now, everyone. Woo!